It's a great pleasure to welcome Ranganathan Gopal Krishnan to give our webinar today. This is our first webinar for 2024. We've moved to perhaps less frequent webinars, but hopefully webinars that really provide a focus for our discipline and really a really good opportunity for students, academics, and partners to hear about the latest aerosol science. So there'll be one webinar per month, and I will give more details about the next webinar at the end of this one. But it's a pleasure to welcome Ranga. Ranga did his undergraduate degree at the National Institute of Technology in India, followed by a PhD completing in 2013 at the University of Minnesota. And I'm sure many of you will be aware of the really strong aerosol research effort that's been underway at Minnesota for many decades. He then went on to do a postdoc at California Institute of Technology, followed by a postdoc at the University of California, Berkeley. And then after a short spell at the University of Iowa, he moved to the University of Memphis in 2016 as an assistant professor and now as an associate professor. It's a great pleasure to welcome you, Ranga. I think maybe if you could put your title slide up, and then so Ranga will be talking about understanding particle behavior in gas phase systems for engineering applications. So Ranga, the floor is yours. We look forward to your talk and being able to have some discussion at the end of your presentation.
Thank you so much for the opportunity to address this audience, and I'm really excited to do this today. Thank you. So if you see the title, I kept it intentionally broad to kind of tell you that we are trying to do this in as many systems as we can, which can be classified as aerosol. Now, if you think about gas phase particulate systems, the conventional definition is that aerosol is a system containing of dispersed particles in a background gas, which is where I started my research career looking at aerosol charging problems as part of my doctoral research. As a faculty member in the last few years, my group has been focused on many different systems, which will still fit with this broad definition. And that's what this is the biggest message that I want to send out to all the doctoral students here. The word aerosol is a really broad tent. If you care to look at it in a sort of abstract and general way, a lot of systems can fit into that definition. Okay, so we are looking at ionized gases where processes like charge exchange and recombination take place at the molecular scale, like angstrom scales, and modeling those reactions is one of the focus of our research. At a slightly higher length scales, we are also interested in what are called dusty plasmas, which is basically like if you walk on the street, there is dust in the air, we just call it dust or aerosol or as you see it. But if you disperse those dust particles in a plasma, they exhibit very interesting behavior, which leads to a lot of self-organization and collective behavior, which is part of our investigation. And then we also are interested in how powders can be dispersed using ultrasonic techniques, which are very efficient in doing them at high concentration and making them really steady. So as you can see here, all of these applications kind of fit within the definition of aerosol. They are interaction between particles in a gas, and that's the broadest view that I'm trying to take here. So I'll start my presentation with talking about dusty plasmas, which are more like statistical physics experimental systems or model systems to understand how electrostatics work at a really basic level. So for those who are uninitiated in this topic or are hearing this for the first time, you know what is a plasma. Most of us know that it's an ionized gas. It contains ions, electrons, and background gas molecules. And to that mix, if you add some dust grains, which could be nanometer size to micrometer size, these dust grains predominantly become negatively charged. Why? Because if you think of it as a running race, ions are much slower than electrons. Electrons can zoom around much faster. They charge any surface that is present in the plasma to a negative charge or negative potential, and they basically turn every grain into a negatively charged grain. And these dusty plasmas are actually present a lot in everyday life as well as in the universe. you think about the features found on Saturn's rings, these are all charged objects that are also orbiting the planet. They are an example of a dusty plasma. Dust is also formed in semiconductor manufacturing when higher energy radiation or ionizing radiation is used to etch away surfaces. These vapor that are ablated away rise up, they cool down, they form particles. Those particles become charged, they organize above the wafer, and they are basically contaminants in that context, which basically have to be mitigated. And the other major area or headache where dust is a problem is in fusion reactor devices. As we know, fusion is getting a lot of push of late, and when we are able to conquer fusion, or when we are able to make energy out of these plasmas, that energy is going to be absorbed by the walls of the fusion reactors, which will cause them to thermally crack, degrade, and be released into the plasma as dust. And that dust can soak up most of the energy produced and basically kill the whole process. So as we are trying to say that fusion will be the future, we are also trying to plan ahead for that, saying that we need to understand how to control this dust, otherwise this will never get off the ground. So these are all the motivations. What we are doing is something much more like on a fundamental level. So if you think about the dusty plasma, I told you it contains dust, electrons, ions, and neutral molecules. We are interested in the processes that happen at the surface level or at a particle level, where if you are a conventional aerosol scientist, you know what is charging or coagulation. And we are also interested in how mass, momentum, energy, and species are transported to the surface of a particle. Think of the particle as the receiver. We want to model what happens about these transport quantities to that particle. And you are doing pretty much some of that in an atmospheric context. If you are an atmospheric scientist, or if you are in an indoor air quality person, or if you're trying to do like drug delivery, all this is what you do at a fundamental level, but our context is plasmas. That's it. And our applications are in semiconductor manufacturing, materials production using plasmas. And if we zoom out a little bit, look at like a length scale that spans around tens of microns to maybe like a millimeter. I told you these grains are all negatively charged. They do self-organize and exhibit collective or phase behavior. So we are interested in, if they are a phase, can we define a thermodynamics for them? Can we describe their transport in terms of field quantities like viscosity or conductivity and so on? And how exactly does multi-body dynamics actually work at a nuts and bolts level? And that's what I'm going to talk about in the next few minutes. The applications of this type of work is in basic physics. We want to use this system as a model system or a controlled experiment to understand statistical mechanics, and also to understand how dust transport takes place in fusion reactors. So these are some of the broad goals of what we are trying to do. So I'll start here and just go a little bit deeper or give some more details of what we do. So if you think about the dusty plasma, I told you there are many grains, and each grain is negatively charged, and we'll assume that they all have like a charge of Zp. And depending on their number density, we can define an average spacing between the grains. And based on that, you can work out what is their average potential energy. It's like asking, if I have a grain here and a grain here separated by some distance, what is their potential energy? On the other hand, they also have a velocity. You can see this movie here. Now, if I didn't tell you anything, what you would think is this is just some flow that's being visualized. On the other hand, this is actually a set of microparticles which are moving in a plasma. And when visualized, they look as though they are a fluid. And if you are a fluid mechanics person, you would say that there is a velocity in this direction, there is a velocity in this direction, and there is a velocity gradient going on here. So this is exactly true, except there is no fluid. It's the collection of particles that behave like a fluid. So if I take their instantaneous velocities and average it, I can define a temperature for them, just like you would think of a temperature of a substance. It's their kinetic temperature based on their thermal energy. And if I compare these two, that is, if I get a ratio of the potential energy to the kinetic energy, I can define what is called in this field as coupling constant or electrostatic coupling parameter, gamma. And just think about it. If gamma is much less than 1, meaning if this quantity is much higher than the numerator, that means the system behaves like a gas. And that's what you learn in your thermodynamics 101. A gas is something that has almost entirely kinetic energy and almost no potential energy. On the other hand, if you just zoom across to the other end, you see that gamma much greater than 1. That means the numerator is much greater than the denominator, which is like saying I have something that looks like a solid, because a solid is almost entirely potential energy and almost no kinetic energy. And that's what you learned in solid mechanics or solid state physics, where your atoms are all bound in place. They have very less mobility. They can just jiggle around wherever they are. And this dusty plasmas is basically a model system where you can create either set of particles that behave like gases, like liquids, or like solids, and use them for basic science experiments. So that is where the history is coming from. And I'm not saying I discovered all this. All this is basically known from since the mid-90s, when the field came into existence. And there are a lot of review articles that you can actually take a look. So dusty plasmas are a nice classical analog of quantum matter. Think about real matter. There is atoms, there is molecules, there is quantum mechanics that governs their interactions. In the system that I showed you, what I have is large microparticles which are charged. So they behave or they interact through electrostatic forces, which is purely classical. There is no quantum mechanics here, but we can reproduce a lot of the macroscopic phenomena that you see in everyday life. So we can use that system to visualize processes like diffusion, shear flow, turbulence, phase transitions. You can create a microscopic laboratory of particles, of microparticles, which you can see. That's the big difference between this system and real matter, where real matter, if you have a beaker of water, you can't see all the molecules. There is no microscope in the world yet that can visualize all the molecules at the same time. But in the system that I show you, you can see all the microparticles. They are behaving like a liquid or like a solid. You can actually make theories about how they should behave and use the data, that is the trajectory data, to verify your theory. So that is the power of this system, where you can use it for understanding condensed matter phenomena. So what we do here, we take that data. Data is our gold. We try to get data from wherever we can. We use openly available sources, which is becoming a trend in science, where people now understand that we don't have to confine the data to only the lab that generates them or the group that generates them. Publishing your raw data or curated data open source has become more prevalent, at least among the funding agencies. And then there are also collaborators that we work with. They do the experiment, we do the modeling, and we try to analyze them together. We also go to user facilities in the US, which are funded by the Department of Energy, where we are allowed to spend extended periods of time, work with their staff, build experiments, come back and do the analysis. This way, we don't have to own the infrastructure there. And then we also have our own lab where we do experiments that are more niche and more specialized, that we want more control than what a user facility or a collaborator would allow us. So we do everything to get data. So we start with data. And today I'm going to talk about one of our experiences at a user facility in the US and what kind of science that has led us to. So this game is a long game. We have spent nearly 2 years trying to build a relationship with Auburn University. They have a lab called Magnetized Plasma Research Lab. They have a very big infrastructure to do plasma experiments. So I've been sending my students over the last 2 years to go there, learn about the experiments, spend semester after semester trying to build the experiment. And now we have something worthwhile that my student Ravi is holding here. We are going to talk about what he developed in the lab and how that is going to help us do basic science work. So some basics. If you think about a plasma, I told you it contains dust, or we introduce dust. And if we make sure that the dust is of the same size, they all become charged and they all going to have like their weight pulling them down. And because they are negatively charged and this electrode has a negative bias, they are going to also feel a levitation force that is pushing them upwards. So when these two are in balance, and if all the grains are of the same size, they all levitate in a single plane. So you can actually confine them to a monolayer, a literal monolayer, where all of them are in the same plane. And if you look at them from the top, they are going to behave like they are a two-dimensional material. So that's the basis of what I'm going to say today. They are a two-dimensional material, okay? Now, if I look at it from the top, so what I'm showing you here, henceforth, is the top view. Okay, we are less concerned about the side view, because I'm going to show you some proof that ensures that the side view is exactly one monolayer thick. So if I look at it from the top, if we vary the plasma conditions like gas pressure, electron temperature, electron concentration, we can get the charge on each grain to be just enough so that it behaves like a gas or like a liquid or like a crystal. So these are all pretty much the same type of same particles, same dust particles with the same size, but by tweaking the knobs on the plasma, we are able to get them to behave differently in corresponding to whatever their charge. So this was the starting point of our say. We are trying to say that yes, we can realize different states. Now we want to do more analysis on this. So these movies, you can acquire them with a camera based on the frames and frame rate. If you're into photography, what you're going to do is basically take 2 frames, get the difference in position divided by the frame rate or the time, and that's going to give you the velocity, and then you can do the second derivative, the acceleration, and so on. So the data that after all the experiments is really trajectories, which are position and velocity time series of the grains. And that is where the analysis starts. Using those positions and velocities, you can calculate the structural description of these collections. That is, you can say whether the structure looks like a solid and what's the signature of a solid. If you are a solid state physicist, you will say that it has a repeating lattice, it has certain kind of periodicity. Or if it's a liquid, it's more amorphous. There is like a pair correlation of finding certain particles at a certain distances. You can think about how they exchange momentum or thermal energy through collisions. So those are what called autocorrelation functions. And then you can also think about like thermodynamic quantities, which describe their collective behavior as pressure, internal energy, temperature, entropy, and so on. Or if you can also think about their transport, they behave like a fluid. So if they have a viscosity or do they have a thermal conductivity, all of this can be calculated from trajectories. So if you know the trajectories, anything else is just a matter of computation. So we get these trajectory, and I'll just skip this part because for today's, actually I need this. So we get the trajectory and we summarize those trajectories as what are called distribution functions. So distribution function is like saying, if I have n particles, say n is a large number like 3000, I can ask the question, how many particles have their velocity and position in a certain range? And that would be the density or phase space density of that combination of position and velocity. And you can map out where the particles are located, what speed they are moving. You can classify them. This is literally binning or creating a histogram of particles based on their position and velocity. You can not only do F1, you can also do F2, meaning you can say how many pairs of particles have their positions and velocities in certain ranges, or how many triplets, quadruplets, up to n can be any integer, basically. So we are going to use these type of phase space density functions to group our data, because we handle a lot of data. You can think about if there are 3000 particles, each have two components of position and 2 components of velocity. That's going to be a lot of numbers to handle. So the physics question we have in mind is, these grains are all highly charged. So each grain, I told you, is negatively charged. It has a charge of around like negative 10,000 units. So they are very highly charged. You can see on the picture here, they never really get very close to each other. That's because they have a strong repulsion going on between them, that they never will actually touch each other. They might just scatter off of each other from a distance. Now, you know that like a 2-body collision modifies the velocities of 2 particles. We are asking the question, as the strength of this force between them or the coupling between them increases, not only 2 particles, but multiple particles might collide with each other simultaneously. It's like a multi-car collision. They all scatter off their momentum and they all repel away from each other. So that happens in these type of systems. So our goal is, how do we describe these collisions? That is, If say, if you are in high school, your physics teacher is telling you there are two particles that are coming in with a certain initial velocity, and your goal is to compute at what velocity will they rebound off of each other, given that it's an elastic collision or inelastic or whatever collision. The same problem, literally the same problem, we are now asking, what happens if 3 particles come, 4 particles come, 10 particles come? We want to develop an understanding of how multi-body collision works. And if you actually do the mechanics, the equations, you can see how complicated this can be, given that the incoming velocities follow a distribution. The other particles, that is the neighborhood, also follows some kind of a spatial distribution. There are so many things that can vary that you can't do this like a high school problem. You have to do this like a statistical problem, and that's where this becomes not mechanics but statistical mechanics. So that is all me. That is, in the sense, I try to understand, or I try to come up with the question what we want to study, and the next few slides I'm going to show you what my students did to make that possible, because all I'm doing is telling them that this bullet point, this is what we want to do, but what they do is do the hard work of actually making it happen. So what we did was to this is all the work of my students I'm talking about. So we tried to create a dust cloud. We drop particles in the plasma. I told you about their levitation. And if you see here, it's not exactly that they are all of them in the same plane. Some of them are below and above, creating a quasi two-dimensional structure, which is not desirable, because what I want for the theory and modeling is perfectly two-dimensional structures. So that is where the problem starts. So then what my student Ravi worked on is to take these quasi 2D layers. He wanted to remove all these unwanted grains so that they can be, we don't have to worry about them on the modeling side. And he developed this control arm apparatus, or like an electrode, where he can actually use so this, if you imagine like the plasma chamber, he can use the control arms from outside to tilt the electrode, to move the electrode, so that all these extraneous particles can be reflected away. And what we get is something that's crystal clear, perfectly two-dimensional. So this was basically entirely student-driven work. So here's a video. I'm going to keep quiet for 1 second. So what you're seeing here is the levitating cloud above the electrode. The electrode is being moved around to selectively remove some particles, to selectively push away all the off-plane grains. And in the end, we are able to get better two-dimensional clouds. So this is happening in real time when the plasma is on, when the dust is already levitating. And using the control arms, we were able to get something that is exactly two-dimensional. If you look at it from the top, you don't have to worry about what is beneath or above. There is no beneath or above, it's only 2 dimensions. So here's the top view, here's the side view, where we are able to confirm this and then move on. So then, with not only removing those off-plane particles, we are also able to actually remove one particle at a time. So if I see here, I'm going to play this video again and keep quiet for 1 second. So what you just saw is that the cloud containing like 21 particles was moved to the side, and then one particle at a time was removed. And we can do this all day to get n equals 4, n equals 25, n equals 37, whatever number we want, because that selection of number comes from our statistical mechanics goals that can be achieved with the method that has been developed here. So this is to get precision control in the number of grains that are in the cluster. It can be n can be 1,000, n can be 40, n can be 5, whatever we want it to. So using this technique, we were able to start with a two-dimensional monolayer and keep removing extra particles as needed to get high selectivity in the number of particles in the cluster. And as you can see already, that there is already a very interesting structural problem here, in the sense, if you see there is like a, if you think about your the first model of the atom that you heard about, the Thomson model, it had what is called as a core and shell structure. So there is a core of one particle, and then there is a first layer, and then there is a second shell. So you can think about the first shell here has 2 particles, the second shell has 8 particles, and so on. So we can use this methods to study classical electrostatics, statistical mechanics, and now I'll come back to the theory angle or the modeling question, which is, so here is basically an assembly of the electrode arm as it is installed in the plasma chamber, and this was all work done at Auburn University by our students. And this is Ravi and this is Zibo. They together developed this electrode arm. So as you can see, the work is not just modeling. It is also on the experimental side. The goals can be interchangeable. Sometimes the experiment drives the modeling, sometimes the other. So coming back to the theory or the modeling question, I don't want to go deeper into this very ugly looking math equation. But what I'm trying to say is, if you have a system of particles, you can track their velocities and positions using what are called as distribution functions. I talked about that briefly before. So we can write an equation that talks about how F1 changes over time because of collisions, because of forces, because of velocities, and also because of interactions. That is, when 2 particles collide, their velocity changes. When 3 particles collide, their velocity changes. So what are the contributions of different types of collisions to the change in, say, n equals 1, n equals 2, and so on? So that is really the classical problem in statistical physics or plasma physics. It's called developing the collision operator. And a lot of theorists have proposed collision operators. This is one example of such a collision operator that came out in 2019. Our approach is to be data-driven, get experimental data from dusty plasmas, use that trajectory data to develop these type of collision operators, and then publish based on them. So that we'll have what is something that is experimentally validated or based on experimental data. So our goal is again to tease out these collision operators. So for example, if we trap 2 particles, we can let them exchange their momentum and try to use the velocity data from this 2 particle cluster to develop what is like a binary collision operator. We can do that for 3, 4, 5, and so on. I didn't show all of them, but we can show, like, if we have a cluster of 15 particles, we can look at how they exchange momenta between each other, or how their velocities change over time. We can do this with good control. That's really the message I'm sending out here. So we are trying to tease out these collision operators from the data, and that is the work in progress, where we had this foundation laid by Ravi, where he got a very good device that can produce exactly controlled number of clusters. And now we are trying to use it to generate data and then work with the data. There's a lot of analysis that we need to do moving forward. So overall, the focus of this type of work, where we understand phase-like collective behavior, is to develop a thermodynamic and transport framework for dusty plasmas. So if you are in the 18th century and you are just encountering water or air, you are trying to develop an equation of state. You want to understand how its transport properties like viscosity change over time. This work is exactly analogous to that, in the sense we treat this dust dispersed in a dusty plasma as a material. And if it's a material, can it have an equation of state? Can it have models of transport coefficients or values of transport coefficients? And that's the overall goal of this these type of investigations. And these have been supported by several grants from Department of Energy and US Army. And our goals or application areas are broadly to study non-equilibrium statistical mechanics, which is basically to study classically interacting particles. And then we also want to use dusty plasmas to do materials production at high throughput, like kilograms per hour type quantities, so that the dense conditions where we can load a lot of dust particles or a lot of precursor leads to multi-body dynamics. And our fundamental work is trying to understand that multi-body dynamics. And if we understand it, as engineers, we want to apply it to produce materials. So that's sort of the segue to the next set of applications, what we do. So I talked a lot about dusty plasmas, and in my this systems slide where I have other types of systems. Now I want to talk a little bit about this what we do. We did a few years ago on powder technology, and the question here is these are the students who worked on it over the years, and funding came from FedEx Institute of Technology. The need, the starting point for this work came from our need to disperse ceramic powders as aerosols so that we can use them for another process like spray coating. When we started this work, we realized that ceramic powders are actually very sticky. If you spread them on a surface, they are almost impossible to be removed. Even if you use a moving part like an impeller or a blade or a fan, what they do is they lift up and immediately they coat the surfaces, they deposit on the surface, stick to whatever it deposits, and then the aerosol production basically stops. So you get a peak or a burst in the beginning, and then it slowly fades away, and soon you have almost nothing. So our goal was to develop a source of high concentration aerosol from powders that was stable for a long time. We wanted concentrations that are unprecedented, and we wanted stability. All the existing market solutions, firstly, they were very costly. We approached a company that sold a product that would do something similar, and the price was upwards of $40,000, which we could not afford. The other problem was, even if we paid all that, they produce aerosol in a very intermittent fashion. Sometimes you get maybe if you're lucky, you get it for a few minutes, maybe half an hour, and then it suddenly stops or the concentration fluctuates. So we wanted stability as well as high concentration. What we were able to do here, and I haven't talked about this video that's playing here. This conical piece is an ultrasonic transducer, which is sending out ultrasonic waves. And in this picture, the frequency is about 25 kilohertz. And when we adjust the gap distance between the transducer and the powder bed, just enough that the gap distance is equal to the wavelength of the waves, we are able to get the standing wave pattern formed. And those patterns, basically, they carry all their energy at the nodal points, and they lift up the powders very efficiently and levitate them basically acoustically. So this plume here is actually very steady. You can sustain this process for many hours. We have tried that in the lab. What we go is try to go in with a sampling tube and swoop that aerosol, and you can send it for either measurement or for another process that uses this as the source of aerosol. So this was the method we came up with. We started by thinking about how to reduce the number of moving parts, because moving parts leads to a lot of particles getting deposited. We tried to, can we do like with one part? Can we do it with two parts? And then we ended up with this method, which had no moving parts. So it's just a transducer that's held above. It's almost like you are going to do ultrasound imaging. You just put the solution that the physicians use, and then you place your ultrasonic transducer and the mapping is done. We don't do mapping, we are not doing imaging here, but it's still non-contact and it is very efficient. So we were able to publish 2 articles related to this method, how we did the characterization, and then also we were able to get a patent application granted. So we have IP on this. So I'm going to show you a particular so before I show you, so I'm going to show you the step where we adjust the height of the transducer, and when we hit the correct height, you can see that the powder dispersion suddenly goes from nothing to maximum. So I'll keep quiet and play this video for a couple of minutes. So the transducer is being moved up and down to figure out the point of resonance. So once you hit that, you can see that the dust plume generation is very steady, and we just hold it there and send the sampling tube to collect the aerosol and send it further for processing or measurement. So this transducer is driven by a circuit, and it's a very cost-effective solution that we came up with. This just the parts of making this device costed like around $2,000, which we could definitely afford, than the $40,000 that the company said they would charge. So we did characterization of the ultrasonic transducer's output. So we collected the aerosol in a sampling probe, sent it to a Venturi pump, which is basically generating a lot of turbulence so that we can break up the powder particles and then send them off to measurement. And so here's the measurement schematic and the publication from 2019 where we describe this. So we were able to get in the first round with one transducer, we were able to get very steady concentration of titanium dioxide aerosol from powders, commercially available powders. We didn't do any processing, just buy them and put them into powder bed and try the experiment. And we were able to get, more importantly, we weren't able to get high concentration right away, but we were able to get excellent stability. For about an hour, we were able to hold the concentration really steady. So that was very promising, that we understood that we are onto something here. So then we also try to understand if the raw powder and the aerosol particles collected from the gas phase, how they differ from each other. What we figured out is that the Venturi pumps we use for deagglomeration was not highly efficient. So the powder particle breakup wasn't as thorough as we wanted it to be. So you can see here that in each case, in one case, we have a 5-micron powder that is sort of fully deagglomerated. But any nanostructured powder which had primary particles in the nanometer range, like 500 nanometers or 30 nanometers, the individual particles don't detach from each other because those are held together by really strong forces. The turbulence we generated isn't enough to break those bonds. But what we were able to get is steady aerosol production of particles that are nominally micron sized as a whole. I'm not talking about the individual particles. I'm talking about the overall size that is somewhat in the micron size range, which was still a big step forward for us. So then we did improvements to the device. We increased the number of transducers. We used a brush to evenly spread the powder and also to do some milling, so a little bit of pre-processing to improve the dispersibility of the powders we are interested in. And then we did a measurement setup. I mean, basically, we had to produce a lot of the aerosol. And since our concentration now that I'm going to show you was much higher, we had to have like a 2-stage dilution system. So you can see Venturi 1, Venturi 2, so that to get a dilution factor of around 1,000, we needed to do that in 2 stages and then use a TSI optical particle sizer to measure the aerosol concentration or the size distribution, and a DMA system to figure out the size distribution in the nanometer or sub 0.3 micron size range. So this instrument has a range of around 0.3 to 10 microns, and this instrument has a range of around around 20 nanometers to 0.3 microns. So with that, we were able to cover a broad size range. So then, I had that actually, sorry. So here are the results. So if I take the OPS data, we were able to attain number concentrations that are around 1 million particles per centimeter cube. So if you think room air on any given day, if it's pretty clean, it's around 1,000 to 10,000 maybe. But we were able to get 2 orders of magnitude higher. But remember, this is in the micron size range. The OPS range is around, lower limit is around 0.3 microns. If we use the CPC, the condensation particle counter, which has a cutoff size around 2 nanometers, we were able to get around 10 power 7 or nearly 10 power 8 particles per centimeter cube. That is 10,000 times more dense than the aerosol in the room at any given time. So we were able, this is basically like walking through like a low-grade dust storm or a low-grade explosion. So this is really high concentration, which we were able to utilize for other applications. So one of the goals of this, or the understanding that came from this work, was that not only we have high concentration, because they are microparticles, we are also carrying a lot of mass. So this mass concentration, we were able to realize, this is an estimate of based on a number concentration. This was around 0.5 milligrams per centimeter cube. So that is a lot of mass that is being raked up. and can we do something useful with it? That's been the focus in the last year or so, where we are trying to do some applications. So as far as the technology goes, we are at kind of like the level 3, where we just did a proof of concept, and we have ways to go where we want to deploy it in a real environment and do stuff for us. And that's as an example, I'll tell you about what has been on our minds, is related to using this ultrasonic method to do dry powder aerosol delivery, where we want to use this ultrasonic levitation, create a dust plume, sample it with a venturi, and then dilute it with suitable amount of air, and then send it off to a subject, which could be an animal or a human being who is basically receiving a drug, basically the powder, if it's a substance that you want to deliver to the patient. You want to use this as a method to do aerosol delivery. The advantage would be that we can engineer the powder. That is, we can make the powder particles smaller, larger, make it sticky, less sticky. We can do a lot of powder engineering, which is a very mature field within chemical engineering or pharmaceutical industry. We demonstrated that we can hold the plume concentration at a desired level and very steady. So we can hold this steady for hours together. We can always dilute them suitably. And if a patient were to receive a certain drug, depending on how healthy the patient is, we can have the patient be exposed to the aerosol for 1 hour or 10 minutes, depending on how acute their condition is. We can use the exposure time. The physician or the healthcare provider can use the exposure time as a way to decide what type of treatment this patient can have. So altogether, we are trying to say that we can do personalized medicine, but it's the same hardware. It's not going to change from patient to patient. It's just how you operate the hardware, and that means you don't have to do specialized manufacturing. You just do manufacture the same thing and use it for as many patients as you want, but you just have to be understanding how well this device works, which is one of the focus areas currently, and I'm trying to recruit students in this topic and carry this work forward. The other big advantage would be that, unlike current inhalers, which either use carrier particles or propellants or ask the patient to generate all the inspiratory flow, we don't have to do all that. The device is basically like a nebulizer, except it works with dry powders. Okay, I call it dry powder nebulizer. So that is one major application we are interested in. So to wrap up, I'm coming back to the slide that I talked to you about different systems, which can be broadly called aerosols, although they are very specialized. They still can be put under that name. And I didn't talk about these two areas today, but most of our publications can actually describe that. So I'll leave it to the publications. So that is why or what exactly we are trying to do this. What exactly we're trying to do. The how, that is, we are trying to understand the particle behavior in gas phase systems. This is what we are trying to do. And how we do this is that we observe, we do experiments, we do computations, we try to observe what is going on on a physics level. We analyze the data, whether it comes from simulation or experiment. We do a lot of analysis. We theorize, we try to take that analysis, develop or synthesize into models, and then try to go with predictions or make predictions about what should be, and then do experiments again or simulations again to substantiate or synthesize our ideas. And basically, this, if take away from what you from this talk, can be something funny, that you can think about OATS: observe, analyze, theorize, and substantiate, as a kind of a methodology of how we do our research. Now, the most important question is not the what or how, it's the why. Why do we do what do we want to do? Well, two reasons, at least for most of us, that we are curious. Most of us who want to do a PhD are generally curious in nature, so we want to understand the universe we live in. Or we have a urge to save the world. We think that we have a solution to problems that transcend current status quo or current roadblocks, so that we can actually do something and create a difference to the world we live in. Of course, through this picture, I'm not advising any of you to be vigilantes. What I'm asking you to do is think about transcending rules, not the law. All right. So with that plug, I'll just say that I have ongoing recruitment for PhD opportunities in my group. And if you're interested, here's my email ID. Feel free to contact me. And then with that, I'll also thank all my students who are the PhD graduates are currently working in the industry. One of them is a postdoc at Minnesota. And then my current PhD students who are a great bunch, and master students who over the years, and undergrads who have been a very vital part. They bring that raw energy into the group, including one high school student. We have a team that supports each other, and acknowledgement to all the funding agencies for supporting us and all my collaborators. And that's it. Thank you.
Thank you very much, Ranga. A very, very interesting talk that covered some really interesting engineering applications. So if you have any questions, please do either post them in the chat or raise your hand, and I will endeavour to keep track of anyone who raises their hand and invite you to come off mute and ask your question. So we have one question in the chat already, Ranga, that's come to me, and it's in your ultrasonic dispersion.
Sure.
Do you get charging of the particles during that process?
Yes, we believe we do. In fact, we didn't do any measurements yet, but when we try to do like a very simple test, put like a charge, put like a metal surface with a bias, or just like a metal surface next to the powders. Some of them stick, some of them run away, which proves that they might be charged, but we haven't we haven't gone deeper into quantifying the charge levels. That's on our to-do list, definitely. Thanks for the question.
Okay. Thanks, Ranga. I had a question about the first half of your talk, and these beautiful images of these arrays of particles. I guess one thing you're assuming in your analysis as well is that they're all uniformly charged. They all have the same charge. How do you achieve such a uniform charge, such a narrow charge distribution?
Right. So in conventional atmospheric aerosols, we generally think charge as a distribution, in the sense they have a mean value nearly around 0, say a bipolar distribution, and they might have +5 to -5 to +5, or +10 to -10, whatever. In dusty plasmas, that is still true, but the mean levels are so negative, like it's -10,000 units, and the width of the distribution is sort of like 20 units. So it's 20 units over 10,000 units, which makes that distribution's width somewhat less important. So for effective purposes, we treat it like a single value, even though technically speaking, yes, it is a distribution. And when we do simulations, we let in the simulation, we let the charge of each grain to fluctuate as per the ion and electron fluxes they receive. So in the simulations, at least we try to account for that reality. But at least in the experimental data, for simplicity, we go with a number like -10,400, and that's it.
Right. Thank you.
Yeah.
Do we have any questions from the rest of the audience? We have another question in the chat. So the purpose of researching the dry powder nebulizer is to make a commercial version of the apparatus. Is that your eventual aim?
Definitely. That is, this is right now like a method, and even at that, it is still to be tested on at an in vitro or a animal or a clinical level. So right there, that is about 10 years of us testing and validating it. Eventually, we want to package it to a OEM standard, so that this can become either a clinical tool that can be used in a hospital setting, or it can be that used in respiratory or pulmonary research. That when they are experimenting with animals, the problem that I've come to understand is that many groups that do this work, they have their own methods to produce their aerosol. there is no standardization across different research groups or different labs. So if we have something that is standardized, a way of delivering dry powder aerosol, it will cut some of the redundancy, and that's where we want to go. But that journey could take several years.
And I found it interesting. You showed, I mean, you showed the images of these titanium dioxide kind of aggregates, and so those you really don't break up. You end up with micron-sized particles. But this aggregation, I mean, this presumably depends quite strongly on what you're trying to drive, nebulize in this way, and also I guess what the relative humidity, for example, will be. So I guess there are some potential variabilities in that there which need to be understood.
Humidity is a huge factor. It can actually lead to clumping, and the dust will behave completely differently in dry and high relative humidity conditions. That is something to be wary about whenever anybody is working with powders, I agree. In terms of de-agglomeration, in this work at least, we weren't concerned too much about engineering the powder. We bought something which we could find and used it as it is. But if it is to be used in a more focused setting, like for example, if we are running a powder handling facility that is a raw feedstock for some other process, then there would be tighter control on the powder, and some more work is definitely needed on the de-agglomeration. Either the powder has to be engineered such that the primary particles are less sticky to each other so that they are easier to be separated, or we have to make the powder or we have to produce more energy in the venturi pumps in terms of the turbulence, so that energy can actually break these bonds. Now, one thing that we have understood is that these primary particles are stuck to each other because when they were formed, presumably in a flame or a plasma, they were at high temperature, their interfaces were molten and they got stuck. Unstucking them and at room temperature is next to impossible unless you have like a mechanical milling or beads mill to do that work for you. Doing that with only fluid power is next to impossible, is what we found. So either people have to come up with a magical way to break up this agglomerate, or it has to be manufactured in a way that this problem can be sort of bypassed. So that's where we are right now. So I'm not really giving you any solutions. All I'm telling you is the problems we faced.
Thank you. Do we have any other questions from the audience? So I have a question. To what extent can the dusty plasma be manipulated in terms of phase, specifically as a solid type material? Can specific lattice structures be selected for structural defects and atom steps introduced, doping with particles of different composition, etc.? So I guess how far can you push this analogy with the solid phase?
So the solid phase, at least in laboratory experiments, different types of symmetries have been observed, like FCC, BCC, and so on. How that is achieved is whenever you are having this plasma condition, that is, if you have your electron and temperature and concentration, gas pressure, these are the variables that ultimately influence the grain charge. So the physics understanding of how to go for a particular charge through these are reasonably well understood. There are theories that using which you can compute the charge given the plasma condition. So you can design your experiments pretty well. So if you think about the system, the dust is what you can see, but the dust also has the background gas. The system also has the background gas, the ions and electrons, which you can't see. If you increase the gas pressure, the gas is basically flowing over all these grains and slowing them down. It's easier to achieve solid or crystal-like states. So there are several degrees of freedom we can use to realize specific conditions. The field started as introducing like monodisperse spheres. Now people are asking, how about we introduce a bimodal distribution of spheres so that we start getting these different alloy-like behavior, or we can start putting particles that have Janus-like structure. One side they are of one material, other side they are of some other material. So they undergo preferential alignment. So all that creativity is now starting to come out. This field was somewhat discovered in the mid-90s, and since in the 20-30 years in between, we have understood all the basic concepts. Now material scientists, maybe, I think, at least I'm taking interest in using this to study material behavior.
Thank you very much. So I think we'll draw the webinar to a conclusion. I just need to would like to advertise the next webinar. So the next webinar will be in 4 weeks' time on Thursday, the 15th of February at exactly the same time. And our speaker for that webinar will be Professor Lindsay Marr from Virginia Tech University. She will be talking about the effectiveness of ionization against bioaerosols in electrical. And I'm sure many of you will be aware of the work that Lindsay has done through the pandemic. So I hope you'll be able to join us for that webinar. Thanks for joining us today. And thank you again, Ranga, for a really marvelous talk and first talk for our 2024 series.
Pleasure is mine. Thank you.
Thank you. I will stop the recording.
Thank you.